This is question number 8 from the SACE Stage 2 Physics Course Companion from Chapter 2.1 Electric Fields. Here we have the three charges Q1, Q2 and Q3 shown in this arrangement. First we need to work out the magnitude and direction of the net electric field at Q1 due to charges Q2 and Q3. So here we're just going to be using our expression for electric field strength. So I'll call it E2, V1 on 4 pi epsilon naught Q2 on R squared, which here will just be 9 times 10 to the power of 9. Q2 is 1.5 millicoulombs. Milli is 10 to the power of minus 3, and the distance between the two is, at this point here, is 0.6. So over 0.6 squared, which if we substitute into our calculator, we get 3.75 times 10 to the power of 7 newtons per coulomb. We do the same process for Q3. So here I'm just going to call it E3 is 1 on 4 pi epsilon naught Q3 on the distance squared, which here is 9 times 10 to the power of 9 multiplied by 3.5 millicoulombs all over 0.8 squared, which if we substitute into our calculator we get 4.92 times 10 to the power of 7 newtons per coulomb. Now here we need to work out the magnitude and direction, so we need to add these two electric fields as vectors. So here the electric field is defined to be the direction of the positive charge would move if placed in that field. So the field due to Q2, a positive charge will be attracted to that because it's negative. Similarly, a positive charge would be attracted to Q3 because it's negative. So we can draw a vector diagram. Here we have E3, here we have E2, and so the net electric field will be in that direction. A little bit later we'll work out the angle theta in here, but to work out the magnitude of the net electric field at that point, we're just using Pythagoras' theorem. So we have the net electric field will just be the square root of 3.75 times 10 to the power of 7 all squared plus 4.92 times 10 to the power of 7 all squared, which if we substitute into our calculator we get 6.19 times 10 to the power of 7 newtons per coulomb. To work out that angle we can redraw that vector diagram. So here's E3, here's E2, there's our net electric field. We can also shift E3 so it's over here, so now it's a little more obvious how we're going to work out that angle. We have the opposite and hypotenuse, so we can use trigonometry. So we can use tan theta is opposite over adjacent, so theta will just be the inverse tan of opposite over adjacent, which is the inverse tan of 4.92 times 10 to the power of 7 over 3.75 times 10 to the power of 7. These will just cancel out, but if we substitute that in, we get 52.7 degrees below horizontal if we assume that this here is horizontal. So now we have both the magnitude and the direction of the electric field at Q1 due to charges Q2 and Q3. So that's not too bad. It's a little bit tedious, but the calculations are fairly straightforward. Finally, we have to work out the magnitude of the force acting on Q1. So we're just using the relationship F equals EQ. We've already worked out what E is. That's the 6.19 times 10 to the power of 7 newtons per coulomb. The charge here is going to be the charge Q1. So that'll be just the 4.5 times 10 to the power of minus 3 coulombs, and if we multiply those together, we get 2.79 times 10 to the power of 5 newtons, or if you're using the exact values all the way through, then you'll probably end up getting 2.78 times 10 to the power of 5 newtons if you use exact values. But there we have it. That's not so bad. So working out the electric field is fairly straightforward. You have to be careful with the prefixes with milli or micro or whatever it is you're using. Pythagoras' theorem to work out the magnitude of the net electric field. Trigonometry to work out the angle, and then finally F equals EQ for the force acting on our charge, Q1. And that's it.